Or do you want to just go alone?
It's fine, but he's also from China, so
Okay.
yeah, I don't know.
I mean, it's fine if you want to spend time.
I don't know whether he
Yeah, it's okay, it's okay.
don't worry.
Yeah, it's
Here, like, just, you know, that if you ignore, like,
Yeah, so and he also has a PhD.
Okay.
So he's coming from like
Okay.
yeah,
Sure, no, I get it.
Yeah, and that's also interesting. He's doing something related to this. He's doing this nuclear stuff. I don't know what that's
you take HC and then you just start, you know, sweeping out. The gap doesn't scale. I would expect it to at least stay the same.
Even though you're working on exactly.
So here you're saying it's
Probably not worth it.
Yeah, this looks like it's. Well, I mean, like, it looks like a numerical.
Then maybe
I mean, you can't really tell how that maybe it's the other way.
I think the problem is
I don't know.
you have the
Maybe I'm not really saying. Okay, so when I actually ran it, it
questionnaire
scales like
your
L.
email that Sarah sent out last week.
It looks like a straight line, but I don't know.
And then this is something called man-made sun. And people in this area say 50 years ago, after 50 years, we started nuclear fission.
Oh, wow.
But then today, they tell people after 50 years, you have to launch a
So 50 years ago, they said, you need another 50 years.
Apparently, this is the one everyone has.
Yeah, that's pretty.
I did like 640. For this one, I did like 240. Yeah.
I mean, there's no conservation law.
Hold up. Okay,
did you check this? Saracen out? Just in case you want to add
First paragraph.
Yes.
From 2 years ago.
Yeah.
Yeah, tell me.
Okay, yeah. Yeah, that's like beauty.
I think the rest of it is fine.
So let me just start by quickly summarizing what I've done. In the first lecture, I've introduced the experimental platform involving atom arrays, which are excited in Rydberg states, and talked a little bit about what kind of phases we can access with the system, and actually already started talking about probing on equilibrium many-body dynamics with the system, and specifically I first focused on this kind of near-adiabatic evolution involving the so-called Kibble-Zurich mechanism. So at the end of the first lecture, I described what this Kibble-Zurich mechanism is about, and it's essentially a kind of a hypothesis which combines these ideas of kind of growing correlation length and decreasing energy gap, and it basically predicts how the correlated domains should grow depending on the speed with which you cross quantum phase transition. And basically at the very end, so I went through the slide. So basically the idea here is the following, so that if we now, in our system, if we start in disordered phase and basically go across the phase transition and sweep the chemical potential, or it's actually detuning in our case, linearly, and I think that's actually very important that it's a linear sweep. So then this Kibble-Zurich mechanism provides the prediction for how the length of the typical length of the correlated domains should grow with the speed, or with the inverse speed, with the with which you cross this phase transition. And the prediction is that it should be a power law scaling with this so-called Kibble-Zurich exponent, which is basically a combination of mu and z. And for Ising phase transition in one dimension, these critical exponents are very well known, and the prediction is that the Kibble-Zurich exponent should be 1/2. Now this is kind of different from the classical prediction, which should be 1/3. And the question is, can we probe this in the experiment? So basically, the way how we do it is precisely following this recipe, which I just described. So what we do is we change our detuning linearly across the phase transition in the way how it's shown here. And what we do is we basically vary now the length over which we do this kind of linear sweep, starting from a long time where this speed is relatively slow to increasing the speed. And what we do then, we look at the correlation function, second order correlation function, which basically in this case in the Z2 ordered state is just corresponds to this kind of up, down, up, down, up, down, up, down, and it decays. And this characteristic decay here in this case is about 5 sites. So is a quantity which gives us the average kind of length of average domain, ordered domains. So what we then do is basically plot this, we extract this psi, the typical correlation length, and plot it as a function of this inverse speed or the time with which we cross the phase transition. Actually, some of the very first data that we took already, they actually matched beautifully to this kind of power law prediction with the power law exponent of close to 0.5. And that's basically a kind of verification of this Kibble-Zurich mechanism. So at this point, one could just say, okay, this Kibble-Zurich prediction is basically, valid, it's correct. So everything is good. So we can just enjoy our kind of, agreement. But actually it turns out, as with many things in physics, if you start looking at these things a little bit more closely, actually the things are much more subtle. And one of the things, for example, which we decided to check is we decided to check this kind of concept of universality. So basically, the idea is that not, this concept of universality tells us that basically that the physics close to the phase transition should be kind of scale invariant. So basically, if you rescale your kind of parameters with this according to this Kibble-Zurich exponent, like for example, if you scale this the length according to the Kibble-Zurich exponent, all curves should lie on the top of each other. So not only this Kibble-Zurich mechanism predicts that there is one quantity which should grow in a specific way, but this kind of universality tells us that all of these correlation functions should be basically identical to each other. And that's the kind of stuff that we started playing with. And actually, indeed, so here is maybe 10 different curves, which are basically taken at a very different speeds. They result in very different correlation, average correlation lengths. However, if you now rescale the space with this Kibble-Zurich exponent, all of these curves really lie on the top of each other. And it's very good, because this is what this universality tells us. That's how things should behave. However, if you now start kind of looking at this curve a little bit more closely, then what you realize is that this exponential decay, the simplest possible kind of thing that you can come up with, is not a good description of this data. So this data, by the way, is again this up, down, up, down, up, down. And what you see is that, initially maybe it's exponential, but then not only this kind of, there is a deviation from exponential, so this kind of correlation function actually turns negative. So there is like a phase slip, basically. So we can actually kind of zoom into this part, and actually we can do maybe a little bit more. So let's now, this was this up, down, up, down, up, down. Let's just multiply the down points with the minus sign, and then again rescale everything with this kind of, with the Kibble-Zurich exponent. So, then these two curves collapse on each other. But, nevertheless, what we see is that these collapsed curves, so the universality works extremely well. But, but nevertheless, this correlation function turns negative. And actually, I must say, when we first saw it, we were kind of puzzled a little bit because it's really not so clear why this happens. But then we have started also doing some numerical simulations. So this is a result of time-dependent matrix product simulations. I will describe later on, what exactly the techniques which we are using. But what you see is that this simulations reproduce this experiment kind of quite nicely, and indeed here also the correlation function turns negative. So, but then actually it turned out that some of these things are not exactly unexpected. So there have been actually 2 theoretical papers which in fact predicted effects like this. And actually, these 2 papers, they're kind of, looking at the same aspect, but in a kind of very different system. So one of them was an early paper by Leonid Levitov and one of his students, where they basically looked at this Ising transition, at dynamics and quenches in the Ising phase transition in an exactly integrable model. And in this integrable model, actually studying dynamics is still non-trivial. So it involves the so-called Toplitz's determinants. So maybe some of you guys have heard about them. But but they've done kind of like very serious math. And then what they showed is that like to examine basically this Kibble-Zurich hypothesis. And they showed that this Kibble-Zurich hypothesis is in principle, holds, but this what they observed is this kind of non-exponential decays. In fact, they predicted that this correlation function should have some kind of oscillatory kind of behavior with the oscillation period, which will scale as a kind of Kibble according to this Kibble-Zurich prediction. But actually, this theory is not exactly applicable to our case, because this was the case of the integrable system. But it turns out that David Hughes, I guess together with 2 of the students here, actually looked at the quenches in the system, which is very similar to ours. I think with the Hamiltonian, which is kind of a version of our Hamiltonian, this hard boson model, and actually they've also numerically observed this kind of effects. So basically, what we see is that this observations indeed yield universal scaling across quantum phase transition, but these correlations don't decay as a simple exponential. And basically what these observations show that there are clearly in a state which we create, there are correlations between domain walls. So this exactly how these correlations behave and the amplitude of these oscillations actually depends on exactly how we do the quench. So there is a little bit of dynamics of domain walls afterwards. But actually, I must say that, we are still, okay, these effects are definitely present, but, I must say that at least based on on the data that we have, it's not yet completely sure what exactly is the physics of these domain walls. And there are in particular 2 effects which can play a role here. One of them can be the fact that the system does not thermalize kind of very fast. So maybe there are some signatures of this kind of integrable kind of dynamics present here. But on the other hand, in our system we have long-range interactions, and these long-range interactions, they would have natural tendency to actually alter these correlations. For example, if you have some energy cost, if there is some energy cost connected to creating very long kind of domain, this can also lead to this kind of example. And I think this in between these 2 kind of mechanisms, I think we don't yet have a clear kind of understanding, but okay, but it's good that there are some theoretical papers which we can refer to. Okay, so that is okay. So that was, so far the physics associated with the simplest Ising transition, and of course, what we would like to do now is, having understood, verified the Kibble-Zurich mechanism in a quantum system, and also, having kind of verified that, having seen that there are some limitations to the simple Kibble-Zurich picture, what we would like to do is we would like to kind of extend this technique and really study more exotic phase transitions. Oh, and actually, maybe one last thing I should note is that we also, by looking at this kind of universal collapse, we can actually extract independently z and nu, just looking how correlations grow as we approach the phase transition, and we actually it's kind of very hard in a sense to measure them both because this like there are sort of large uncertainties on how you collapse it, but generally our results are consistent with the z on the order of nu and then both are on the order of 1. But okay, so this is so far the picture associated with the Ising phase transition, which is very well understood. But what we would like to do now is we would like to explore this entire phase diagram. And in particular, let's focus now on this kind of Z3 and Z4 phases. So in both of these phases, we can measure correlation functions, these second order correlation functions. So in here, for example, instead of this up down, we have down down up, down down up. So basically, the period of this correlation function is 3. So in here, the period of this correlation function is 4, right? Which is basically connected to Z3 and Z4 ordered phase. Now, even though this kind of ordered states are relatively simple, the actually phase transitions into them are actually quite involved. So in particular, if we focus now on the Z3 phase, then this depending on the parameters, you can have different types of phase transitions, and actually one specific type of the phase transition actually is very interesting, is also connected to the theory group here, is a so-called chiral clock model. So, so this chiral clock model, as I hear, this was actually a PhD thesis of David Hughes, so that must be kind of profound and influential. So, but kind of the physics of that, I'll give you a little bit of maybe a flavor of what is kind of involved here is the following. So basically, if you go into the Z3 ordered phase, so the order which we create is this kind of order, where you have, like one Rydberg atom and then 2 ground state atom, 1 Rydberg atom, 2 ground state atoms. So up, down, 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 up, down, 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 up, etc. But so now, if you kind of want to destroy this order, you can have 2 types of defects, 2 types of domain walls. So one of them, let's call it type 1, is a domain wall where basically this atom kind of moves to the left. So basically, so instead of, up, down, down, up, you just have up, down, up. So this is type 1 domain wall. So another one is a type 2 domain wall where basically, you have an extra ground state atom between 2 Rydberg excitations. And basically, you can kind of visualize them on a kind of a clock. So for example, this is the clock pointing, at noon, and this is basically the clock, kind of this domain wall is like a clock corresponding to rotation, counterclockwise, and this is a clock corresponding to rotation of clockwise. And basically, from this kind of blockade physics, maybe you can develop a little bit of an intuition that we actually can create the systems where one of these type of defects is prevalent. So for example, suppose that we are working in a situation where our blockade radius is exactly, is more than 2 lattice sites, let's say between 2 and 3 lattice sites. So in this case, it will be very unlikely that you can create defect of this kind because it's deeply blockaded, right? So you cannot access it, But defects like this would be actually very easy to create. So what it means is that in this case, this type of defect is dominant, and that gives rise to this kind of chirality in this, chiral clock model set. So basically, the transitions, in most of the kind of this phase diagram, these transitions into the free order state will be connected to this kind of chiral clock model system. So here is actually maybe another way now from the kind of experimental point of view. So here are the images, experimental imaging, showing these two types of defects. So this is type 1, right, where basically you have one defect where two Rydberg atoms are separated by just one ground state atoms. And here there is a defect of type 2 where actually you have three ground state atoms between two Rydberg excitations. And actually, I think maybe this clock direction here is different than from the previous slide, but from the previous slide, but this may be not so important. It's arbitrary which way clock rotates, so long as it's chiral, right? So, but you can also look at this, at this kind of chirality aspect by just looking at the domain wall density. So what you see is that, so for example, like so here is the picture how domain wall density varies as a function. Sorry, this is not no axis here, but as a function of the kind of interaction range. So if the interaction range is short, then we are, like predominantly all of our domains are Z2 ordered, and there are maybe, a small density of Z3 ordered kind of domains. So if we increase the interaction range, then the Z3 is a dominant phase, but here, so like we have also an interesting situation. So initially, Z2 ordered kind of domains are the second most probable, but then eventually, they become extinguished because blockade becomes very, very effective. So it's very unlikely to create this kind of Z2 order domain, but for that, for example, you can have higher probability of creating Z4 order domain. So basically, so everywhere except for this point, this kind of our system is chiral, right? So basically what we would expect is transitions into this kind of chiral clock model. So it actually turns out that this chiral clock model, despite its kind of long history, up until recently, it was really not completely clear what the nature of the phase transition into the state is. And in fact, there has been a debate whether this is actually a direct transition from disordered state into this CCM ordered state, or whether it's accompanied by so-called incommensurate regime. So basically, incommensurate regime is where you have basically kind of different types of sort of domains competing with each other. It's actually kind of it's a kind of a little bit okay, my intuition at least about that it's kind of almost like a kind of disorder type phase, but it's not it's not the one where kind of clearly the free order dominates. But actually, the recent work done by one of Subir's student, Ryan, together with Sunwoon and Hannes, actually provided, what at least I'm told is a very clear indication that it should be a direct transition. And moreover, by working with this kind of chiral clock model and basically looking at the kind of the flow of the parameters, this calculation actually extracted both z and nu. And what's kind of interesting is that this z which emerges from this model is actually is neither 1 nor 2. So this means that this model, close to a critical point, is not described by relativistic field theory. So it's described by something very kind of exotic. And what at least I'm told by Subir is that this is like the only known example of strongly coupled phase transition, quantum phase transition, where this which is non-relativistic. But don't ask me any questions about that. You can ask. You can always ask. anyway, so okay, so but for us, you know, what we can do, we can just go ahead and now measure this Kibble-Zurich exponents across all interaction ranges. And basically what we see is we see kind of, you know, three regions, you know, three kind of plateaus. One is this Z2 plateau, which we already discussed. Actually, in this Z2 plateau, we see, I would say on average, we see the Kibble-Zurich exponent slightly larger than 0.5, maybe on average something like maybe 10% larger than 0.5. So, but then we see also two plateaus, you know, which is one is associated with the Z3 phase, and another one which is associated with the, you know, some with the Z4 phase. Well, for the Z4, it becomes much harder to actually measure and extract this correlation length, which is kind of reflected in error bars. So, so there are a few things which we can say about this. So first of all, we see that, you know, this Z3 plateau, which is actually close to theoretical prediction for this chiral clock model. So which is kind of, you know, about 0.37. So this kind of Ising phase transition is in general is a little bit larger than 0.5, but we actually understand it, you know. So in particular, this is also this, you know, matrix product, time-dependent matrix product simulations yield the exponent slightly larger, around maybe 0.55, and we believe that this is a combination of the long-range interactions and kind of finite size effects. So, so there has been some theoretical papers showing that it's actually once you have long-range interactions, is that, you know, to approach, you know, truly kind of universal exponent requires a really large system size, and we are working with 51 atoms, so it's actually not that big. We also observed this kind of a plateau, which seemingly corresponds to this transition into Z4 state. But at this point, I think this nature of this transition is in debate. So most people believe that it goes through this kind of incommensurate phase. But like, you know, what will happen with Kibble-Zurich there is not completely clear. So I should say that we also observe some region where this Kibble-Zurich scaling does not hold very well, and these are these kind of regions where we most likely either don't cross the phase transition at all, or we go into this incommensurate phase. And in this case, we don't expect power law scaling. Actually, transition into this incommensurate phase should be of Kosterlitz-Taulis type, you know. So, okay, but so that's kind of the current status of this work. So what you see is that we can really, you know, like, you know, have tools here to really study, you know, make almost like precision measurements of this quantum critical phenomena. And, you know, I expect that this work will be actually, you know, kind of extended now over many different other transitions and for studying this kind of, you know, phenomena. Okay, so at this point, I'd like to kind of move on and talk about far from equilibrium dynamics, but maybe I pause here and ask if there are any questions. So it kind of, well, it started out simple, but ended up maybe a little bit on a kind of complicated side, but is everything, yeah.
Can you explain again why the correlation has become negative?
So, okay, so phenomenologically, we believe what happens is that there are some, you know, correlations between domain walls here. So the domain walls are not just kind of, and not just distributed kind of randomly, but in some way there is kind of like a repulsion between domain walls. Right, and that causes this basically phase slips in the correlation functions. But what is actually maybe not completely clear is what is the cause for this correlation for the domain walls, and I think there are two kind of effects which might be playing a role. one of them is connected to the fact that, so this system that we work with, they're not an integrable systems, but as I will describe in a little bit, they're actually kind of special. So they are kind of, if you want, weakly ergodic. They are weakly ATH. So they thermalize very slowly. So maybe these are these kind of consequences of this, of this slow thermalization. But another, explanation is connected to this kind of long-range interactions. So imagine, for instance, that you are now like in Z2 phase, but approach the kind of phase transition. So what happens is that it's energetically costly to so like in the ground state, it's clear will be up, down, up, down, up, down. But if you're not looking at the ground state, if you're exploring kind of neighborhood of the ground state, then there is some energy cost associated with the this kind of structure, up, down, up, down, up, down, due to the second nearest neighbor interaction. And what is clear then in this case, if you start, building kind of a domain, up, down, up, down, up, down, up, down, so eventually the cost associated with the next nearest neighbor interaction can become very high. So it might make sense for a system to relax, to maybe skip one excited atom, right? And that would kind of intuitively at least introduce this extra, this phase slip. Does it make sense? No? So this is, okay, this is explanation. Okay, I can describe, so, okay, so basically what is going on? So, and this explanation is very simple, but I just don't know if it's right, if it's kind of correct and if it's relevant. So specifically, so imagine, so basically what we are doing is we are looking at the other domains. Which ideally should be like that, right? And if this interaction, if this model would have short-range interaction, if only the relevant interaction is this, right? Then of course this is like, this is a perfectly ordered structure. It has zero kind of energy cost, right? But imagine that you now have second nearest neighbor interaction, which is non-zero, right? So what happens in this case, there is certain energy cost to having this kind of structure, right? And basically, so if you have a domain length, let's say this is like 1, 2, 3, 4, right? If you have 4 kind of ordered pairs, right? So there will be some energy cost associated with this, I plus 2 will be times n, right? Will be an energy which is associated, with this kind of with this domain. So basically, and the idea is that if this domain becomes kind of too, and it has to be compared with whatever, with kinetic energy, which it has to be compared with some other energy scale, characteristic energy scale, right? And so basically the idea is that like if you are not, if you're now crossing this kind of phase transition and you are looking, not necessarily in the ground state, but you're looking at what sort of characteristic, domain length that you create. So it might be that at some point when kind of n is sufficiently large, it might make sense for the system to skip one excited atom, right? So you could have state like this, and then the domain here starts again, right? And so that would introduce this kind of phase slip, right? In principle, right? And I think this is a plausible scenario, but to be honest, we just don't know if this is really what's going on here, because because this effect is also present in systems, integrable systems without long-range interaction. So these are these two, and actually in the systems without long-range interaction, so the origin of that is I think the fact that they don't just don't formalize because they're kind of integrable. So you have everything is sines and cosines in kind of coherent systems. That's my simple interpretation. Yeah.
How much is change into detuning compared to initial detuning? It's 10%, 1%, or something.
No. So here we go all the way across phase transition. We start with the negative detuning. So like everything, so basically what sets so this is like our initial Hamiltonian, right? So it's a Hamiltonian like this, which is basically kind of I sigma x plus this, delta ni plus v ij and I and j. Right? So we basically measure everything in terms of this the Rabi frequency, which is basically a transverse field. And so typically in these experiments, we start with delta kind of negative, and absolute value is much larger than omega. So it's maybe, I don't know, 5 times, 10 times larger than omega, and then go to a positive value with the opposite sign, but it's also much larger than omega. Okay. But it goes, this phase transition is around the point where delta is actually is positive, and it's actually on the order of omega. It turns out not quite at 0, but this pushes it. So that's what the phase diagram, for example. So what you see is that basically all of this phase transition, they occur for kind of positive values. So sorry, there is no scale here, but it says delta over omega. So they all occur at positive values of delta, right? And we make sure that we go well in the ordered phase. Yeah.
So as you cross the phase transition, do you see the correlations like plateau, but also the correlation length plateaus, or no?
Yeah. So let me just show maybe one slide. I can. That's typical. That's a typical kind of example. So what we see is that as we go across the phase transition, the correlation length starts to grow, right? But then for given speed, it kind of saturates, right? And in this case, it's kind of maybe relatively simple cases. Sometimes it's saturated. You see there is a little bit of dynamics, and this dynamics depends exactly on on what we do, how deep we go in the phase, and so on. But this is like a characteristic behavior, and actually. This is, for example, that's how we extract both z and nu. So what we do, you have, basically length, and here is the tuning. You can be rescaled in the time units, right? And when we, rescale them with the z and nu, that's where we get this kind of nice collapse. But but I should, yeah. So that's a kind of typical observations.
The speeds at which you are limited by your decoherence and by, I don't know, experimental.
That's right. So that's also a very good question. So so as I said, so we kind of work in a regime where we, in the entire array over entire kind of duration, we make maybe on the order of 1 error, right? Which actually should not. At this point, it should not kind of limit us, right? Because so the way we work with 50 atoms, but for many of these experiments, we actually, to get rid of edge effects, we actually take, maybe a group of like, 40, 45 atoms. And the kind of typical correlation length, what you see we observe is in a range of maybe 5 to 10. It's actually kind of doubles effectively, so it becomes more like 20 correlated, 10 to 20 correlated atoms. And what you see is that, okay, now in the array of, say, 40 atoms, if you make, maybe 1 or 2 errors, you are still kind of within the range where they shouldn't limit on average your correlation length. But if you make many more of these errors, it becomes problematic. So, and I think for the Z2 transition, I would say it's under control. I think these transitions in Z3 and Z4 phases, they are more fragile. We clearly see that. And for example, also like they're actually more fragile, they're actually also harder to simulate with, for example, matrix product states. And so I would say there we see good qualitative agreement with matrix product state simulation, but the quantitative agreement is not as good, And actually what's surprising is that our experimental result is closer to the kind of predicted scaling exponent, for example, for Z3 state than matrix product simulations. And this is somehow not fully, I think, not fully clear to us why. So it's kind of always, it's a little bit dangerous thing to talk about new work in the school setting, but I hope you guys are all very well educated, Princeton theorists. So. Okay, any other questions? All right, so let me then, in this case, let me go forward and talk about another experiment which we have done already with the system, and that includes really looking at dynamics far away from equilibrium. And this is actually one of the first experiments we have done. We published experimental result last year, but actually the theoretical interpretation is still the subject of current debate. And actually, in addition to Hannes and so on, there is some group of people, all Princeton alumni at different times. They are actually thinking about, basically trying to understand these results. So, okay, the experiment that we have done is illustrated here. Is actually very simple. So far, what we have done, we've looked at this kind of adiabatic following across this transition. We just changed the tuning slowly and basically entered these ordered phases, up, down, up, down, up, down. And so in this case, for example, for 5 atoms, you create this a state where basically, we have 3 atoms in a Rydberg state, and 2 atoms, it's up, down, up, down, up, down. So, but now, once we reach this point, usually we make a measurement, but now let's, instead of making a measurement, do something else. Let's now change the detuning, but do it kind of in an abrupt fashion. So, let's change it across the phase transition. Let's bring it to 0, in fact. So, and in this case, what you would expect is you basically dump a lot of energy in the system, and the system should undergo rapid thermalization. So, as already indicated, our model is not in any, we are not working at least any known integrable point, that's, would be the expectation. Actually, it's one of the first experiments we have done, and actually what we observed was surprising. So specifically, so this is a state, up, down, up, down, up, down, but then if we now quench this state, if we quench the tuning to 0, what we observed is something like this for this small system of 5 atoms. What you see, okay, clearly, this initial order kind of disappears, but then actually there is some kind of structure in this the evolution. So let me kind of zoom in for you for a few specific points. So, for example, if we wait a little bit here and zoom, for example, on this point, what we observe is that instead of up, down, up, down, up, down state, we end up with state down, up, down, up, down, up. Then we wait a little bit more, and actually we recover something which looks like an original state. And these oscillations, keep going. So I must say, when initially we observed that, we were actually quite surprised. And we thought, oh, it's probably a finite size effect. 5 atoms is not that big a system size. So let's repeat this experiment on, on 9 atoms or 51 atoms. And so here, what I'm plotting now is domain wall density, right? Density of domain walls which we create. And so what we kind of observe here is that initially the domain wall density is low, then we quench, domain wall density becomes high, so basically 0.5 would be an equilibrium state. But instead of going to 0.5, what we observe oscillations, and these oscillations don't, this curve doesn't even oscillate around the value 0.5. So these oscillations, moreover, occur at a frequency which is actually kind of very odd. It's proportional to our driving frequency, but it's not. Does not occur at this driving frequency, but it's at a frequency modified by something like close to square root of 2, but not exactly. And moreover, the decay time of these oscillations is kind of on a scale which is given by second nearest neighbor interaction. So it kind of indicates that there is some blockade physics here, which probably drives this, and this long-range interaction causes the decay. So, and once we saw it, and it's been already, more than a year ago, we started wondering what is kind of physical origin. So we have in general, kind of non-integrable many-body system, and it should really undergo fast thermalization. So you could say, well, you have this blockade constraint. This is a constrained system. So, you cannot access all Hilbert space. Maybe it has something to do with that. But actually, even for this perfect blockade, the Hilbert space size still scales exponentially. It actually scales exponentially as a kind of golden ratio to the power of n, and this is actually not an accident. So it turns out these kind of models can be mapped into Fibonacci anyon, interacting Fibonacci anyon models. And that's exactly the Hilbert space dimension. But still, this kind of stuff should really result in rapid thermalization. So, okay, so we started kind of trying to understand, what's going on. And actually, one of the things we have done is we tried to model it, and we used matrix product state formalism, a kind of time-dependent matrix product state. So I guess most should maybe ask the question whether people know what matrix product states are. Most people know. Is there someone who has not heard about this? So basically, the matrix product state is a kind of like it's a variational. It's a way to write down variational wave function by keeping track of degree of entanglement that you create, right? So if entanglement is relatively low, then matrix product state should give good result. If entanglement is high, then you need the entire exponential kind of number of parameters to describe your wave function. So what we see here is that basically this matrix product state with large bond dimension really provides a pretty good description. But still, what's the kind of physical origin of this effect? So just to kind of give you a little bit of maybe intuition, a simple intuition. So if we kind of dimerize this system, if we say, okay, let's now consider instead of just looking at the chain together, let's just chop it into pairs. And then each pair will be kind of blockaded pair. So in this case, it behaves like an effective spin-1 system. And according to this, in this spin-1 system, the Rabi frequency will be enhanced by square root of 2. So it is kind of due to this blockade condition. So I will just explain in a second. So if you neglect the interaction between these dimers, which is of course wrong because they should interact strongly, but then you would get these oscillations. These oscillations will be with exact kind of frequency, which is square root of 2. But then there should be interactions between them, right? And so why don't these interactions result in kind of dephasing of these Rabi oscillations? Why don't they result in formalization? So this is kind of, once again, this is this picture. So basically, if you have these blockaded atoms, right, then according, from this blockade constraint, you exactly pick up this this factor of square root of 2, right? That's the one which we discussed earlier in this lectures, right? So it should, there would, this square root of 2 would correspond to nice oscillations, but then these atoms, these pairs should interact, and I think this is, this is not described by this answer. So actually, it turns out there is even better approximation, and it turns out in particular, so you can introduce this matrix product state with one dimension 2, which actually, where you satisfy constraint now on all of these links. And actually, this is a kind of a minimally entangled or this is a locally entangled state. It actually predicts these oscillations with frequency which is correct to within 10%. So, but kind of in terms of the physics, at least, when we published our experimental results, what we realized a few things. So first of all, the oscillations which we observe in these quenches depend very sensitively on initial state. And usually, you would say, okay, what counts is, for example, things like energy density. So, but what one could do quenches with states where all of the atoms initially in a ground state and do a quench to 0. In this case, you don't even cross a phase transition. But in this case, basically whatever coherence in a system, it's very rapidly decaying. Instead, if you start in this Z2 ordered state and quench, that's when this coherence, really exists for a long time. These oscillations are preserved for a long time. So we also at the time start looking at quantities like entanglement entropy, and what we observed is actually, especially for these constrained Hamiltonians, this entanglement entropy grows very, very slowly. So essentially what happens is that these kind of pairs of atoms, nearby atoms, get entangled. But then instead of usually, the way how quantum systems formalize, right, you get, local entanglement, and then this entanglement kind of spreads very rapidly. So but here, what happens is that, you create this local entanglement, but instead of spreading, somehow system comes back and becomes disentangled. So this kind of like non-trivial behavior is kind of what we realized it must be going on, but it's probably due to this constrained dynamics, and eventually long-range interactions, result in formalization. But we really didn't know what's the physical origin of that, and I must say we still don't know. But there is kind of now some interesting insights which I would like to discuss. So a lot of these insights was due to Dima Banin and his friends, Max, for example, Serbin, Zlatko Papic. So they actually made a connection between this observation and something which is called quantum scars. So what are quantum scars? So this is actually a concept from the single particle chaos. So the paradigmatic example of the single particle chaotic system is the so-called is the so-called billiards. So in these billiards, basically, as you can see here, kind of most of the trajectories are completely chaotic. So you kick the particle in one way, and it just starts exploring the entire sort of space, of the system. So and this classical chaotic trajectory basically also, when you quantize it, it kind of results in a quantum chaotic system. However, it turns out that in these billiard problems, there exists some small number of trajectories which are actually closed. So, for example, this trajectory is closed. So this trajectory clearly is closed. The particle will bounce back and forth. This trajectory is actually not stable, and so you can check it by just if you have some small deviation from this trajectory, it will completely deviate. And this is that's the nature of chaotic system. So and initially people thought, okay, so like this kind of closed trajectories, once you quantize the system, they will have no role, they will have no effect. But actually, it turns out that this is not the case. So it was actually Eric Heller, who is our colleague in Harvard Chemistry, initially pointed out that connected to this classical unstable trajectories, there are quantum eigenstates which kind of resemble with classical periodic orbits. And basically, the condition for the existence is something that people kind of long debated, and I think this is, I don't know if it's still a completely closed subject, but basically the kind of the intuition for the existence of these trajectories for these eigenstates is the following. So if you have, if your classical periodic orbit has a period t, right, and if you now then estimate, for example, characteristic Lyapunov exponent, that's how rapidly this kind of trajectories would diverge if you go away. So if this period t times the Lyapunov exponent is actually much smaller than 1, right, then this kind of classical closed trajectory is not a bad approximation, at least for some time. So in this case, at least in a single particle chaos theory, this is what results in these so-called quantum scars. So what Dima and his colleagues then pointed out is that there might, this kind of phenomena which we actually observe, might be related to this concept of quantum scars, and these are basically some many-body states which are embedded through this thermalizing spectrum, but kind of exhibit robust dynamics. So, for example, so if you kind of take this Z2 ordered state and just look at the kind of overlap with different states, what you see is that you have very little overlap with kind of majority of the states, but there is this kind of band of states which is actually periodically which is evenly spaced, to which it sort of projects. This projection is the largest, and this is basically this kind of special set of states which really plays a role in this dynamics. And actually, in their picture, they sort of thought about this, quantum scars, maybe like kind of trajectories in a Hilbert space rather than a real space of the system. So actually, when we first saw this paper, I must say we were not completely convinced that is really kind of a solid argument. But then we started playing with this kind of matrix product states, and actually, if you make use of this matrix product states, kind of as a variational wave function, you can actually make this analogy with scars kind of much more rigorous. So specifically, what is plotted here is this is a trajectory in this kind of generalized space parameterized by 2 angles, but this is a matrix product state, so bond dimension 2. Actually, I have it maybe on a. Sorry, so I have the equation on the next slide, and what we see is that in this kind of subspace spanned by this matrix product state with bond dimension plus 2, there exists indeed a trajectory, an unstable trajectory, which corresponds to this kind of collapses and revivals which we observed. And kind of as a kind of characteristic Lyapunov exponent, what you could do, you could look at a kind of a leakage out of this subspace, right? Because this subspace is a kind of in a Hilbert space is just some kind of special hyperplane. So we can ask how rapidly system leaks out, and then indeed it turns out that the leakage, is actually for these trajectories is relatively slow. So I would say there are many interesting questions that now are still being kind of debated. So, for example, what is real true origin and what are the conditions for this quantum scars? So, is this model really generic or is it somewhat special? And I will comment on that. So, there are some indication that this model is not completely generic. It's maybe, sort of proximal to some non-trivial integrability point. So can one generalize these considerations to other constrained systems? In fact, the answer to this question is yes. So in fact, we're able to generalize it to classes of many different, for example, high spins Hamiltonian. So this phenomenon is still present. And there are also some kind of very interesting ideas, as actually Daniel is our colleague, a string theorist, who is thinking about sort of dynamics, kind of dual dynamics in kind of quantum gravity. And for example, his kind of hypothesis that maybe this kind of quantum scars correspond to something like Kepler orbits, where particles, in this dual gravitational theories then go around black holes. But okay, I'm not, qualified to really, answer this, to comment on this.
Well, what is a typical lambda in our system? What is a typical lambda?
So so the typical like lambda t is about 0.2.
Lambda itself.
So this is not, it's smaller than 1, but not much smaller, you could argue. But it actually turns out you can make this number yet smaller. And maybe I can here, so let me just comment that this understanding this quantum scar is actually ongoing work. So let me just, tell you about, a couple of papers which are on arXiv related to that. And then maybe comment about some of the very recent developments, which are sort of almost off the record. So there are two papers I want to point out. One of them is this, is this understanding this using this matrix product state approach, and this is already I basically just described it. So the way how we can construct these matrix product states intuitively in the following. So what if you start with just the product state ansatz for individual spins, but then project this product state ansatz into the constraint space. So this projection will introduce some correlation, introduce some entanglement, but it actually turns out that this entanglement can really be described in terms of this matrix product states, and this matrix product states can be just parameterized by two variables, two angles, and that's how we end up with this trajectories, and basically, so that's this kind of hyperplane picture. So this 0.2 is basically a probability to kind of leak out, if you go across a trajectory, right? And so that that results in this kind of basically very slowly decaying kind of oscillations. So what Vetica and Anusha and Chris noticed, however, is that they looked at the kind of bulk spectrum of the system, and what they noticed is that this bulk spectrum, although sort of kind of non-integrable, it's only very weakly ETH. It obeys ETH, but it kind of converges, the level statistics converges to thermalizing statistics very, very slowly. And somehow, this smells like proximity, maybe to integrability or something like this, but there is no known integrable point in the proximity to the specific point where we do the quench. And actually motivated by these considerations, Vetica started thinking about this kind of more generalizations of this Hamiltonian by adding some other terms. So this P is a projection operator, projection to the ground state, kind of to satisfy blockade constraint. This basically X and Z is just X and Z rotation. So our original Hamiltonian is just PXP. Now, she's adding, for example, second nearest neighbor, kind of Z interaction. So they're kind of like a long range interaction. And actually, it turns out that by introducing a relatively small perturbation, you cannot find an integrable point, but you can make the statistics much more Poissonian. So you can make the system even sort of less formalizing. And the question is, and this is like a property of the bulk, and this, maybe suggests that perhaps the system, after all, is somehow is actually is somehow just close to integrability, and maybe that's the origin for this kind of oscillations. And I would say that the verdict now is still not yet out, so it's kind of I think this is still ongoing work, but I hear that the recent indications point out that this kind of point kind of close to integrability is actually not the point which actually maximizes this oscillation. So by playing with deformations, you can actually find this scar-like trajectories where leakage is extremely small. So it basically can be kind of almost close to zero with some kind of numerical precision. And this is not, but this is a point which actually where the system formalizes quite rapidly. The bulk of the system formalizes quite rapidly. So anyway, so this is actually a kind of open direction where maybe some of you can still contribute, and maybe kind of coming back. This is exactly when I talked in the beginning about really studying this, understanding the systems far away from equilibrium. That's an example of the kind of phenomena we would like to really look for. We are pushing the system, exploring these corners of Hilbert space where no one else has, stepped yet, and we are trying to understand kind of what's going on. So, how are we doing on? Yeah. So let's,
is there any reason why we are avoiding mean field Hamiltonian and solving explicitly for total time density function or something?
Well, the entanglement here plays a role. So the mean field, you need some degree of entanglement. So basically, this matrix product states this kind of description is, I would say, as close to mean field as you can, come, right? So this is basically, this is a state with minimal entanglement required to satisfy this blockade constraint, right? So if you want, these are these mean field trajectories, but they require entanglement, at least local entanglement. But I guess the surprising, it's sort of, to me, like the surprising thing is usually once you create this local entanglement, it just keeps, exploding, right? And this is not the case in this kind of models. So these constraint models are kind of strange, right? Yeah.
What's the number of quantum scar scale with system size?
It's exponentially small, right? So this number of this kind of special states, it's maybe, so it's maybe one could see it from the kind of like, sorry. So this special kind of band of states, which is somehow separated from the bulk, right? It scales linearly with the system size, where everything else, of course, exponential, right? And it's actually, that would be consistent with this classical scar trajectories because it's the same thing. So the number here of this classical stable orbits is actually linear scales linearly with system size, and it's a small fraction, it's exponentially small fraction of all trajectories. Yeah.
At the point where the oscillation is most significant, is this system chaotic?
What's that?
Is this system chaotic?
So yeah, the point where the question is the point where these oscillations are most prominent. Is the bulk of the system chaotic or not? The answer is yes.
But you have the entropy growth is very slow, right?
But it's for this only the special states. So any other state that on generic state you quench, it will go. It's still constrained system. So in a sense, I'm sort of hesitant. It's for sure a base ETH, but it's maybe still kind of weakly ETH. But it's, yes, in that sense, the base ETH. So it's chaotic. But that said, these kind of deformation ideas they're really new. Like this particular kind of ways to look for this, to enhance the scars or to look for integrability is really a new way. So it's a paper posted, less than a month ago, and I think there's already elaboration on that. So it's kind of it's a very modern topic of the research. Yeah.
How important is interactions to see these many body skulls? Because if you look at the classical analogy, it's just a non-interacting particle bouncing.
Yeah, that's right. So of course, that's a difference between basically quantum and classical. system. So I mean, if the particles would be non-interacting, then no one would be surprised if you have perfect revivals, would be Rabi oscillations, right? So, and this would be like, would correspond to just integrable Hamiltonian in this sense. So here interactions are, I would say critical, because they really provide for, they result in entanglement, they result in integrability, right? And that's what it makes it non-trivial, But I guess maybe what the point that we're learning here is, these constrained interactions, constrained systems are kind of special. So unusual kind of logic does not maybe necessarily apply to those kind of systems. Yeah.
So for the quantum stars, we specialize the Z2 phase, right? But is there anything interesting if we go to the Z3 or Z4 phases?
Yeah, so there are generalizations. And already mentioned that there are generalizations involving higher spin, for example. So I think there is at least one scar-like trajectory which we found for Z3, but I'm not completely sure. But they are hard to find. There are two ways you can kind of generalize the system. Generalize this consideration. One involves just like looking at a normal constraint model, just increasing the spin. And another one, you can use this kind of correspondence to this Fibonacci kind of diagrams. You can also use it to build a family. That's so far the only two kind of examples that we know. So we know that there are examples, but we don't have a systematic theory or a picture for those. So, okay, so I think there is a 5-minute kind of warning here. So maybe I would like to kind of finish maybe with somewhat lighter outlook. And, it's maybe a little bit of the kind of describing where this work is going. And in particular, I would like to maybe make some interesting connection, which I think next 2 years will be kind of very exciting field of research. So what we would like to do here, of course, kind of on the technical side, we would like to improve coherence. We would like to improve individual atom control, like to extend the system to D. So we would actually like to experimentally start measuring entanglement. And, this kind of questions which we were talking about here, how does entanglement grow? We would like to experimentally probe that. We already have some early indications, experiments looking into that, and it actually looks very, very interesting. So I mentioned that the system which we study has some connection to these Fibonacci anyons. So I didn't have a chance to elaborate on that, but it turns out one can map it to a system of interacting anyons, kind of very much along the line that of the kind of Microsoft Station Q paper, I think it was maybe 10 years or so ago, where we had these Fibonacci chains. So there are some, of course, we would like to, as we scale up, we would like to keep errors under control. We're thinking about error detection and correction. There are also new ideas, new experiments with novel atoms. There are actually 2 experiments now with strontium by Manuel Landers and Adam Kaufman. And actually here at Princeton, there are also 2 kind of new Rydberg experiments also. One involving kind of like a conventional atom, I don't know, rubidium maybe, or lithium, by Basim, and another one was ytterbium, exotic new atom, which offers also new possibilities, by Jeff Thompson. But actually, one thing that I would like to kind of really point out is a connection that these studies have with an important problem in quantum computer science, and this is a problem involving implementation of optimization algorithm. And the way how I would like to point this connection is by basically noting that this kind of Rydberg constrained Hamiltonian, which we have sort of been discussing for the past 2 lectures, has one-to-one mapping to a very well-known optimization problem, one of the classic optimization problem, which is called maximum independent set. So what is maximum independent set? The idea is the following. Suppose you're given some, undirected graph which consists of vertices connected by links. And basically, an independent set is a set of these vertices which is not connected by, in which each of these vertices is not connected to another one in this set. So in other words, if we now, for example, color these vertices red, we can color only those things which are not connected directly. So that's what's called independent set. So, and maximum independent set problem is very simple. You just need to find the maximum for a given graph. You need to find the maximum number of vertices which you can cover, which you can color. So, for example, this is an independent set, this is an independent set, and actually for this problem, this is a maximum independent set. So this is one of the, one of these problems which are very easy to formulate, but actually very hard to solve. In fact, it is NP complete problem, it's NP hard problem, and in fact, even finding approximate solution for this general graph is NP complete. But actually, I would like to maybe, give us one specific example of this problem. So one example involves the maximum independent problem on a so-called unit disk graph. And this here, the idea is that you have this kind of vertices which you connect with links. And you only connect those vertices which are within certain distance, within distance d. So at this point, we end up with the figure which looks like kind of a network figure. And this is something that you can probably see in the back of your airline magazine when you travel next. And what it kind of indicates is that this problem is practically important. Moreover, it turns out that this problem on a unit disk graph, to at least find the exact solution, is also NP hard. And actually, if you followed my lectures, more or less, then what you realize immediately is that this problem is very much reminiscent to the problem of a dipole blockade, where this D is just a dipole radius. And you base what you would like to do here, you would like to excite as many Rydberg atoms as possible, subject to this dipole blockade constraint. So indeed, this solution to this maximum independent set can be actually encoded in a ground state of the Rydberg blockade Hamiltonian. And essentially this kind of phase transitions which we have been discussing throughout most of these last 2 hours effectively corresponds to kind of solving this maximum independent set problem. But so far, of course, we solved it for relatively simple graphs. Right? So, in particular, if you look at this kind of two-dimensional networks with the atoms, put in with certain proper density in some kind of disordered location, that actually can be used to encode some really hard, some very interesting maximum independent set problems. And now the question is, how can we, solve this problem? So there are 2 ways how one can approach it. One is by doing this kind of adiabatic evolution. That's the essence of this adiabatic algorithms, or sometimes called quantum annealing algorithms. While another is more dynamic method, and there is this class of algorithms called approximate quantum optimization, which actually through this kind of series of quenches of the kind which I described, it can really be used to try to find, basically it's kind of a variational approach. You try to find variational approach which will minimize, in this case, energy of this blockaded Hamiltonian. So, what this means is that there is a very nice connection here between this kind of quantum dynamics and quantum optimization. And actually, we've now started already kind of going towards this direction. So these are some first images of two-dimensional systems which we now can create, and we start already sorting the atoms. I mean, there is also some very nice work in 2D and 3D, also in Paris and in Penn State. And basically now kind of the goal is to combine our sort of high fidelity control over the systems with this kind of 2D, disordered arrays, and try to really explore dynamics and try to see if we can solve some optimization problems. So I think that's really an exciting frontier where this many body dynamics and quantum optimizations are very closely connected. Understanding these dynamics, especially this non-equilibrium stuff, would really help us with this quantum optimization. So I think I used up my time. So this is a summary of the lectures so far, and I'm happy to take any questions.
Well, if there's no questions, then take
Yes,
a
we
10-minute
can
break.
resume tomorrow. Yes.
I like it.
Some of these things like C3 is interesting for theories. Maybe it's